Next, we have the variance and standard deviation. So these are more complex but more powerful measures of variability. Variance is a measure of the spread of recorded value on a variable. So the larger the variance, the further individual cases are from the mean. The smaller the variance, the closer the cluster around the mean. So to calculate variance, we start with the concept of deviation. So the distance from each individual score from the mean. So if for example the IQ is 110.54 is the average, and someone has an IQ of 102, then their deviation is 102 minus the mean, which is 110.54, which gives us negative 8.54. So someone with an IQ of 115, for example, will have a deviation of 4.46. If we just added up all the deviations, we'd get 0 every time, because that's a mathematical definition of the mean. So instead of doing that, we square each deviation to eliminate the negative signs, and these are called the squared deviations. So we add up all the squared deviations to get the sum of squared deviations. Okay, which is in the case of the IQ example, we get 2825.39. Finally, to get the variance, we divide the sum of squares by n minus 1, because here we're using a sample. So for class A, we get 235.45 for the variance. Okay, now the problem with variance is that it's in squared units. So in this case, our data is in IQ points, so the variance is measured in IQ points squared, which doesn't really mean anything. So that's why we usually don't report the variance by itself. Okay, instead we take the square root of the variance. Okay, so we report standard deviation, which for class A will be 15.34. Now this makes sense. The standard deviation of 15.34 means that on average, people's IQs deviate from the mean by about 15 points. So that means something to us. That's meaningful. Now standard deviation has some important properties. First, a larger standard deviation means more variation around the mean. Second, a standard deviation of 0 means all values are identical. So you have a constant, not a variable. Third, if you rescale a variable, say by changing unit, the standard deviation changes by the same magnitude. And fourth, like the mean, standard deviation is affected by outlier. Okay. So the standard deviation is very important in statistics because it forms the basis for so much of what comes next in inferential statistics. When we do hypothesis testing, construct confidence interval, or calculate z-score, standard deviation is central to all of it. Next, we have percentiles. A percentile is the value below which a percentage of data falls. For example, if you're at the 80th percentile on the SAT, this means that 80% of test takers scored lower than you. To calculate which value corresponds to a given percentile, we use this formula. N is equal P over 100 times N, where big N is the total number of values, and P is the percentile we're trying to get, and little n is the position of that percentile. So let's say we have 20 test takers, and we want to find the 20th percentile. So we calculate 20 divided by 100 times 20, which equals 4. So we'd look at the fourth value when our data is sorted from low to high. Now, percentiles are particularly useful in education and medicine. When your doctor tells you your child is in the 75th percentile for height, that means 75% of children that age are shorter. When a college tells you the middle 50% of admitted students had a SAT score between 25th and 75th percentile, they're using percentiles to describe the typical student. So let's look now at how variance and standard deviation matter in the real world. Let's look about salary and inequality, for example. Imagine a small company with an annual payroll of 200,000, and their salaries are 100,000 for the president, 50,000 for the manager, 40,000 for the secretary, and 10,000 for the cleaner. So the average salary is 50,000. That's the mean. The range is 90,000. The variance is over a billion. Okay, but that's in square dollars. But the standard deviation is 32,400. Now the company budget goes up by 5%, so they give everyone a 5% raise. So now the president becomes 105, and the manager goes up by 2,500. The secretary goes up by 2,000, and the cleaner gets $500 more. After the raise, the mean is now 52,500, which is up 5% as expected. The range is 94,500, also up 5%, and the standard deviation 34,000, also up by 5%. Now, the flat percentage raise increased inequality because the top earner got 50% of the new money. The bottom earner got 5% of the new money. So inequality increased by 5% as well. Now, real goods and services cost real dollars, not percentages. So the $5,000 that the president got, maybe can buy a TV every year for the rest of their employment. But the $500 the cleaner got, that's not enough for a TV. So the gap between rich and poor increases in that case. This is why some progressive organizations give a percentage raise with a floor. So like 5% or $1,000, whichever is greater. This reduces inequality instead of increasing it. Let's look now at box plots. Okay, so box plot can show you all the descriptive statistics in one image. So box plot displays the quartiles, the mean, the median, the range, and even identifies outliers. The box itself shows where the middle 50% of your data falls. That's your interquartile range. The line inside the box is the median. This black line right there is the median. A dot or asterisk might show the mean. And then the line extending from the box are called whiskers, which can show you the range. Any point beyond the whiskers are identified as outliers. So in a box plot of the IQ data, as you can see here, you see the box going from 96.5 to 123.5 with a median at 109, and whiskers extending to 82 and 162. So this is a compact way to see the entire distribution in one shot, and it's particularly useful when you put them next to each other to compare different groups.